Good afternoon, everybody. My name is Ben Chaya. I'm broadcasting from the University of Amsterdam, and I would like to welcome everybody to the 7th webinar in the CompBioMed Webinar series, which is run in collaboration with the VPH Institute. I just would like to remind you before we start this webinar that the recording of this webinar session will be put on the CompBioMed website underneath training. So if you need to reference any of the content in this webinar, you can always check on the CompBioMed website for the recording. Without further ado, I would like to introduce today's speaker, who is Dr. Francesc Lebrero Florencino from the University of Oxford. Francesc is a research associate in computational cardiovascular science at the University of Oxford and is in close collaboration with the Barcelona Supercomputing Center. His research topic is the study of multiscale electromechanical behavior of the human heart under healthy and disease conditions. I would like to say one more thing, that to limit the technical problems during this webinar, we ask you to, if you have any questions, please write them in the question module of the GoToWebinar control panel. And at the end of the presentation, I will read each of the questions aloud so that Francesc can answer it for everybody. So without further ado, I'd like to give the floor to Francesc. Thank you very much.
Hello. Just a second. Yeah, so before I start the presentation, I'd like to mention that I intend to speak for about 30 minutes. It will be more or less depending on how I pace myself, but that's more or less the approximate length of the webinar. And well, the topic that I'm going to present is sensitivity analysis of a strongly coupled human cardiac electromechanical model. And I'm also going to be explaining a few other topics related to this, and you'll see in the coming slides. So content-wise, I'm going to give a brief introduction about the heart, a very general one. Then I'm going to explain in a pictorial manner the model, the numerical model, the mathematical model that we use. And then I'm going to go a bit further into each of its components, and then related topics such as how we create our geometries, how we impose boundary conditions, and then I'm going to explain the sensitivity analysis framework that we use, then proceed into results and wrap up with a few conclusions. Okay, so let's start. So one might wonder, why are we studying the heart? So basically, cardiovascular diseases are the first cause of death worldwide, and it's even increasing in terms of prevalence. So every year the number of these sort of conditions increase, and as you can see in this plot over here, it's quite leading, unfortunately. Okay, so when we talk about the heart, well, what do we mean? So the heart, anatomically speaking, is like this. It's composed of 4 chambers, and it's basically a pump, a very sophisticated pump, indeed a pump. Most of the simulations I'm going to be presenting focus on the left ventricle, which is this one here, and what it does, it pumps blood to the systemic circulation system that basically feeds the brain and related organs with nutrients. And another topic that I'd like to mention or to point out is fiber direction, okay, because I'm going to be talking about it quite often, and I want people to understand what it means. So cardiomyocytes, or the cells that form the heart, are arranged in specific directions, okay? And we can see a pictorial a picture of how these directions are arranged. And I'd like also to mention that these directions change throughout the cardiac wall. So basically, they change from this point over here. Hopefully, you can see what I'm drawing to this point over here. Okay. So from a positive angle of 45 degrees to a negative angle of 45 degrees or similar. It doesn't need to be specifically 45, it could be 60 or 70, but around these values, okay? Let me erase, yeah, okay? So just a second, I'm not very familiar with the drawing tools, okay? Yeah, okay, so an overview of the numerical or mathematical model. So the model that we're using is a strongly coupled electromechanical model, okay? Has four main components, two systems of ODEs and two systems of PDEs. The PDEs are basically one that deals with electrical diffusion at the organ level, so at the heart level, and the other PDE is solid mechanics, so the momentum equations, and it deals with, they deal with solid deformation, okay? And the two systems of ODEs are cellular models in the sense that they model, one models ionic activities at the cellular level, and the other one models sarcomere contraction, okay? And although they're usually presented separate in literature, they are actually coupled in the sense that what we do is we couple them together, even though they're presented as two separate entities, they're not. They're coupled together, and the exchange is quantities here, okay? And likewise, the rest of the, sorry about the drawing, okay, and the rest of components also exchange many different quantities. For instance, diffusion is affected by strain, sarcomere activation is also affected by deformation and deformation rate, and so on. I'm gonna be explaining these further, so do not worry. Okay, in terms of continuum models or PDE models, we have these two. So on the left, electrical propagation or electrical diffusion, they're modeled with one of the main equation, which is basically a reaction diffusion equation, the diffusion term and the reaction term over here. And this D tensor is a diffusivity matrix, anisotropic, meaning that it has different diffusivity coefficients for each of the directions, being F fiber direction, S sheet direction, and N normal direction. Okay, I'm going to explain these terms further in the following. And you can see here an example of how these propagate at the whole biventricular level. In terms of solid mechanics, we have these equations of motion in total Lagrangian form, also with boundary conditions. And by the way, now that we can see it here, these quantities written in red are parameters that I'm going to include later in the sensitivity analysis. Okay, so keep these in mind. They're basically parameters of mechanical parameters. They don't have to do with electricity per se. They're intrinsically mechanical. And then to finish, a hyperelastic model, which is basically the tissue properties, the passive properties of the tissue. So these are measured usually experimentally. Another important aspect to take into account is fluid mechanics. So we usually have two alternatives to model fluid. One of them, and probably the most sophisticated one, would be FSI, or fluid structure interaction. This means having an inner mesh in the ventricles that controls, if you weigh the fluid, and it interacts with the mesh of the solid mechanics in a strongly coupled way, so they influence each other. In this study, we do not consider such an approach. We consider Wien-Kessel approach, which is some sort of lumped circulation model. We use two-element one, so you can see a pictorial depiction here, with two elements being the capacitance and the resistance of the Wien-Kessel. And let me just briefly explain how does the pressure of the fluid influence the mechanical contraction of the heart. So basically, in the cardiac cycle, we usually have four main steps or phases, okay? So it starts from this point over here, and then it goes like this. So this isovolumetric phase, because it doesn't change volume, as we can see, but it rises in pressure, is called the isovolumetric contraction phase. When a certain pressure is reached, the aortic valve opens, and an ejection phase begins, which basically means that the blood is pumped out of the ventricle, the left ventricle in this picture. At a certain level, the valve will close, and there will be another isovolumetric phase, but in this case it relaxes. So pressure drops at a certain level, and then at some point the other valve is open, and the ventricle fills up with blood, and then the cycle can begin again. Okay. How it works is like this. I know this is quite a weak equation, but let me just briefly explain what it means. So you can see 5 here. So the 4 ones that I just mentioned are these 4 over here, and this IN phase, it's initiation phase. What we do is we bring our system to end diastole by increasing the pressure linearly up to this value over here, even 0. And this is just a preparatory step. So we preload our ventricle, keeping our volume constant with a pre-stress that sort of matches this preloading pressure. And then when we reach this value, then the rest of the cycle starts. So isovolumetric contraction, which is a penalty-based isovolumetric contraction, ejection phase through this wing castle over here, or this wing castle over here, they're the same. Isovolumetric relaxation, another penalty. This penalty basically means that we're keeping volume constant. We're ensuring that we're keeping volume constant, or as constant as possible. And then a filling phase, which is modeled with a decay equation. Okay. So let me proceed with a brief explanation of the cellular models here. As I mentioned, we have 2 cellular models, but they're actually coupled. So in essence, we would be talking about a single cellular model, but as they are presented in separately in literature, let me briefly explain them. So this is the O'Hara-Rudy model. It models the exchange of ions in the cell, and this one over here models sarcomere contraction. Okay, so this picture that you see here, it has passive and active behavior, but this is because this is a cellular model. What we do when we couple it to a tissue model or a whole organ model, we sort of take these passive contributions out. We only get the active part, and then the passive contributions would be modeled by the hyperelastic law that I showed in the beginning when I was speaking about the continuum models. Okay. So just another brief explanation. This is coupling at the tissue level. So these are the quantities that are exchanged at the continuum of PDE level, in a way. Just to briefly mention, we have 2 separate mechanisms. One is the mechanoelectric feedback, which means how is electrical diffusion affected by solid deformation, and we have 2 separate mechanisms: geometrical coupling, which basically means, okay, we have some strain term. This F is sorry, these F are the deformation gradients, and they arise when we cast our diffusion equation in a deformed mesh. Okay. Then we also have stretch-activated ion channels, which means that when the cells are stretched, so when the stretch minus 1 is positive, if you want, you have an extra current which is added here. And just to mention, this is just to explain these mechanisms, but stretch-activated ion channels are not included in this study. They're in a way included in the code, but not activated. So basically, this G is set to 0. And the other mechanism, coupling mechanism, is excitation contraction coupling model, which is having that stress that comes from the land model added to the PDE. So basically, you have the solid mechanics PDE, in which P is the first Viola Kirchhoff stress, decoupled additively into passive and active. So this active stress would have such an expression like this. And here I say without orthotropic activation, meaning that this component only affects in the fiber direction. And then you have with orthotropic activation, in which you also have components in the sheet and normal directions. These are, so these F0, S0, and N0, they're like a orthonormal, a triplet of orthonormal vectors, okay? So that's important, and this parameter is also included because it is theorized that it actually affects wall thickening, which is one of the quantities that we would be looking at later. So that you have a rough idea of how we create the meshes. So our biventricular meshes usually come from MRI, clinical MRI. So they're contoured like this. And then this would be the hard mesh. And then in some studies, we also contoured the torso. And using a statistical model, you can have like taller individuals or shorter individuals leading to this. In this study, these will not be considered, but as you can imagine, such meshes are important if you want to compute, for instance, the ECG and an approximation of this of the ECG. So you will be placing electrodes on the torso and then computing the potentials in those electrodes and then getting the ECG from there. Okay. So this is the sort of studies that some people in our group do, so that you know at least that we can also include torsos. Obviously, when you're considering mechanics, it is difficult to know what is the behavior of the interface between the heart, heart that contracts, and passive tissue such as surrounding pericardium that does not really contract. So what's the interaction with it? Those are questions that are still being researched. Okay, so here I would like to mention a few more details about the simulations we consider. The numerical methods we consider are basically semi-implicit, meaning that we do not have a monolithic approach, meaning that we don't solve, for instance, all the unknowns in our model would be voltages, displacements, and the state variables of each of the ODE models that we have. If you want to use a monolithic approach, you have to solve for all of them at the same time. That's not what we do. We use an implicit approach, meaning that we solve electrical diffusion and then separately solid mechanics. Okay, so this leads to smaller systems, and it's a bit more friendly from a computational point of view. The software suite that we use is Alya, which is developed at the Barcelona Supercomputing Center. And so that you have a rough number of how many degrees of freedom are solved every time we solve the time step. We're sort of considering 275 to 300 million degrees of freedom. So these are fairly large systems, okay? And in this study, you will see two geometries: an ellipsoid, 40 million elements, and a biventricular geometry, 31 million elements. So these are the sort of depiction of the geometries with the boundary conditions. We have the Wien-Kessel pressure on the endocardium, and then on the epicardium we have an elastic foundation which models what's the effect of the pericardium on the epicardium of the heart. Okay, and same thing here, two pressures, one for each ventricle, and an elastic foundation which does the same thing precisely. And in the biventricular simulations, we have an added extra effect, which is we initiate the simulation in a very specific way. Here, in the ellipsoid, we started homogeneously in the endocardium, while in the biventricular geometry, we started from 7 root nodes spaced very specifically, as you can see in this diagram. Okay, and one might wonder, why do you have so many, 40 million elements or 51 million elements in these meshes? So the idea is that O'Hara body, which is the cellular model that we use for ionic exchange, is very steep. So if you want to actually get conversions in one quantity, which is conduction velocity, how fast this electrical wave travels along the heart, you need very, very fine meshes, okay, to capture the gradient in this voltage spike that you get in the very beginning. You'll see a video of that later, though, don't worry. Okay, so now I'm going to start speaking about the sensitivity analysis approach. Until now, I've just been explaining, the model, because I think it is very important to know what we're talking about when we go to the sensitivity analysis bit. Just to start, I'd like to mention a few aims that we're going to consider. What we want is to quantify how important some mechanical parameters, those that you saw written in red, how important these parameters are on physiologically relevant quantities of interest, these QOIs. And then we'd like to know, what sort of parameter parameter combinations actually lead to physiological results, so to an appropriate ejection fraction, for instance. And then something which is preliminary, and you'll see because this is what we're actually doing now, is how does certain diseases affect contractility at the whole biventricular level. You'll see a video of the simulation of the ventricles with a certain effects of diseases. Okay, in this case, this is just the correlation definition. So what we do is we sample our parameter space with light in hypercube on 100 samples. I mean, we had to consider sort of considerably large number of samples, but not too much because these simulations are fairly expensive. We actually need supercomputers to solve this. So 100 was sort of a compromise already. Then we're gonna study the sensitivity of these quantities of interest versus the parameters by partial rank correlation coefficients. This is the definition of partial rank correlation. But so these are these linear regressions, which basically take into account the linear effects. So they take away the effect of the linear effects of the rest of parameters on the one you are actually measuring in this equation. Okay, and because it's ranked, all our data is ranked, so you substitute the data for the rank, so that the most important one will be the highest rank, and so on. You start decreasing. And this is done because we actually have nonlinear but monotonic behavior in our QOI versus parameter space, if you want. So partial rank correlation coefficients allow for a study of sensitivities under these sort of framework. Okay. Importantly, 4 quantities of interest are chosen. Ejection fraction, as I've mentioned, this is the most important one, clinically speaking, and systolic pressure, epicobasal shortening, which is basically if you have an ellipsoid, you could measure what's a fractional change between the apex and the base, which is that cut that we have. And wall thickening is basically a fractional change of how much your cardiac wall thickens. And I'm just recapping here. So all the parameters that I've mentioned that were written in red, I'm just going to mention them again. So we have the stiffness of the pericardium, which is what's the stiffness of the springs that we use to surround the epicardium. So they're put basically here. And diastolic pressure. So that's the pressure that we use to preload our ventricle. Pressure at the start of ejection is basically the limit between isovolumetric contraction and ejection. Windkessel capacitance and Windkessel resistance, those are the 2 parameters of the Windkessel. Orthotropic stress parameter, this KORAT2. So as you can see, the first parameter, the one that was related to the sheet direction, is not appearing here. The idea is that we found that with just one, you can sort of retrieve some more thickening. So we want to keep it as simple as possible. And then a very important one, which is the active stress scaling parameter. So this parameter linearly scales the output of your excitation contraction coupling model, the LAN model that I mentioned previously. So basically, just by changing this parameter, you can change results quite significantly. And then the fiber angle, which is, if you look at this picture, you have these fibers which are arranged at a certain angle with respect to the base, which is a plane, let's say, parallel to the cut here. And then this angle change across the cardiac wall, as we can see, it sort of goes parallel to this basal plane, and then up to a positive angle at the very interior of the ventricle. Then bulk modulus, which is how compressible our tissue is, and one of the parameters of the hyperelastic law, which is just one, because we did a bit of work previously to sort of assess which ones were most relevant, and we found that this one was amongst all of them the one that had a larger effect on the quantities of interest. And you can see here an example of how the ventricle is contracting, and these arrows depict displacement. Okay, so you can see that you also have some sort of twist, a bit of twist around, which is normal. The first example of results I'd like to mention, this is just typical pressure and volume curves for a cardiac cycle. Okay, so these here mean basically isovolumetric contraction, ejection phase, and isovolumetric relaxation. The initiation phase is not, it's basically here, is not considered, but you can see that it's quite typical that you have an isovolumetric contraction, so constant volume, then it decreases, isovolumetric relaxation, and at some point it would start increasing by the through that decay equation that models the filling phase. And pressure follows a similar a pattern which is basically it increases through isovolumetric contraction in the beginning of ejection phase, it reaches a maximum and then decays until here it should just stabilize again. Okay, so filling phase is not included because all the quantities of interest that we are considering in this study are all they all can be extracted from actually isovolumetric contraction and ejection phase. Okay, but this is a typical curve. So let me proceed. In this plot, what we are seeing are the partial rank correlation coefficients. Let me explain how it works. So, vertical axis, we have the input parameters, and horizontal axis, we have the quantities of interest. Okay, those that are not white are the partial correlation coefficients that have statistical significance. Okay, so I only included those, and I added a plus or minus depending on these, they were positive or negative. And as we can see, so we have like ejection fraction. For instance, T rep would be the most influential parameter. And systolic pressure, we have that the ejection pressure, the pressure at which the system jumps from isovolumetric contraction to ejection, is the most influential one. Apicobasal shortening, which is the fractional shortening of the base to apex distance, with the fiber angle, which makes sense. If you arrange the fiber angle very vertically, it tends to basically bring the base towards the apex, so this makes sense. But in terms of wall thickening, you have a bunch of different parameters, and none of them are like hugely influential, let's say. So this is actually meaning that we have several factors that could influence this quantity of interest. And here you just basically scatter plot of the quantities of interest versus these most influential parameters. I did not include wall thickening because of what I just said, that has so many significant but not entirely influential parameters that I kept those out of the plot. But here what I'd like to say is that so ejection fraction is actually the most important mechanical quantity of interest, one that you can obtain from MRI, and usually it's defined clinically as disease or low ejection fraction, minus than 40%, and normal, so it will be actually 40 to 48%, larger than that. And it is defined as a fractional change of the volume, so this volume here and this volume here. So that's a fractional change of these volumes. And as we can see, what I did is I drew those that are low as gray and those that are normal as black. So here it's basically just a cutoff of 40, as you can see. And then we can see that in the other quantities of interest, these normal and diseased, if you want, are mixed together. So one would expect that end-systolic pressure and ejection fraction to have an inverse behavior, in the sense that the lower ejection fraction, meaning that the more you pump out of your ventricle, the higher the pressure you would produce in the ventricle. But that's actually not something that we observe. It's sort of difficult to assess from here. And the same goes for epicobasal shortening. They're actually all mixed together. So in a way, we don't have a huge correlation between these QOIs, but this is a preliminary study. In any case, we have samples of these Latin hypercube samples that fulfill all QOIs, all the quantities of interest. So in a way, they're the most physiological cases, let's say. Okay, this is just an example, okay, of a ventricular stimulation that we have done, and we're working on this at the moment. Okay, So on the left, you have a case which has a zone, an area of slow conduction. And on the right, you have an area, you probably do not see it very well, but it's just an area of high stiffness, imagine like scar tissue, for instance. And this is just a preliminary study in which you wanted to see what was the effect of having these sort of differentiated areas that could model certain diseases. So this is actually something we are keen on keep doing, and probably even apply a similar approach that we applied the Latin hypercube sample approach to see in a more physiological geometry what are the effects of different parameters. Here, for instance, we have two sets of parameters for the Wing Kessel, so we're adding complexity to the Latin hypercube. So this has to be done appropriately, and obviously some of the combinations of parameters could be a bit pathological in a way that maybe doesn't activate, maybe it doesn't fully contract, maybe these sort of things, and we need to really be careful when we define the ranges of the parameters and so on. Okay, so just to conclude, and I think I've been fairly on time. Well, so just to conclude, one of the things I wanted to do in this webinar was to present a strongly coupled electromechanical model and use a global sensitivity analysis approach to assess how sensitive the quantities of interest are with respect to certain parameters that we consider important or not well studied. Okay, so we focused on mechanical parameters because there's, at least to my knowledge, one very recent paper that has studied the sensitivity of electrical QIs with respect to electrical parameters in an electromechanical model. In our case, we studied mechanical QIs with respect to mechanical parameters and QIs that we considered very relevant, clinically relevant, okay, such as ejection fraction. Something, again, that I already said is that wall thickness is not really dominated by any parameters, so it's a bit difficult to study. We do not know what is the, if you want to put it bluntly, what is the parameter you need to change to obtain an appropriate wall thickness or a physiological relevant wall thickness. That's a difficult question, to be honest. Then the orthotropic activation parameter, which is that KORT2, that probably has a significant effect on wall thickness, but and this is what I'm saying here: active stress versus active strain. We use an active stress approach, meaning that we add this active stress to the total stress, and then we proceed from there. But there is an active strain approach in which actually the strain is decoupled multiplicatively, and that there's a few studies which show that with orthotropic activation in an active strain framework, you can actually retrieve physiological values of wall thickening. So that may be an approach, maybe a limitation of our model, but this is something that we'd like to consider at some point. And then very related to CompBioMed conclusion is that we actually need high performance computing in such study. Okay, so we're talking about tens to hundreds of millions of degrees of freedom, and even though we're not solving our problem monolithically, difficult word. Even if we decouple the problem in diffusion and solid mechanics, that's still quite demanding computationally speaking. Okay, so heartbeat of around 800 milliseconds would be approximately 80,000 time steps. Meaning you have to solve those systems, those linear algebraic systems, 80,000 time steps, 80,000 times at least. Here I'm not considering the iterations that you need to do in Newton-Raphson to deal with nonlinearities. So just to end, a few acknowledgments. I'd like to acknowledge CompBioMed for the funding, basically, and because they've allowed this wonderful series of webinars to take place. I'd also like to thank all my collaborators, people from Oxford, people from the Barcelona Supercomputing Center, and also Archer and PRACE. for allowing me to use their wonderful HPC platforms. Without them, I wouldn't be able to do this work. And yeah, that's basically it. And I guess we have around 25 to 20 to 25 minutes of questions. So yeah, let's start.
Thank you very much, Francesc. So now is the time that this should be open for questions. I see one has come through already, and it is asked. Let me see who it's asked by. Maxandre Jacqueline. She says, thank you for your talk. Were the QOIs taken at steady state? How long have you run the simulation before extracting QOIs?
No, they were not extracted at steady state. I assume that by steady state you mean something like a periodic steady state, as in having run your cardiac cycle for a few times, and then when you see that you do not see the quantities of interest changing significantly from cycle to cycle, then you evaluate them. We haven't done that. We have done that at the first cardiac cycle. Indeed, it should be done at steady state, but this very computationally demanding, and we also have the problem that the numerical issue, if you want, that we are using a dynamical approach. So we actually need to use damping in our simulation, and this means that as you run more and more and more and more cardiac cycles, you have dissipation of energy, and you may see a change. Which is a change of your quantities of interest or other quantities that is sort of difficult to recover. So we're sort of thinking now what other modeling approaches we should be considering to have a system that sort of recovers, for instance, the shortening, the fractional shortening, that it has to go back to zero at the beginning of system. So for that, we have considered maybe we use some springs that model the effect of atria and so on. But no, as you asked, we haven't calculated the QOIs in steady state, but that's indeed is something that should be done in general. Yeah.
Great, thank you. She says thank you. Right now, there's no questions posed, but I have a question of myself. In terms of the electrical diffusion model that you're running, is this considering like a homogeneous material as far as the electrical signal is concerned? I mean, are there any diseases in the heart that will happen because the electrical signals may be going through a heterogeneous material or affecting the electrical signal of the heart?
So in the sensitivity analysis approach we've considered is healthy sort of conditions, healthy behavior, no heterogeneities at any level, not at the solid mechanics level or the electrical diffusion level. The only example, the only example that I have is probably this one. So you have a heterogeneity here, but even those heterogeneities are not really physiological. Let's say you should have like two zones, a border zone and also the scar zone or the ischemia zone, whatever you're trying to model, that actually not only have different diffusion properties, but also conductances in the cellular model, or even you may also have mechanical problems, as in electrical and mechanical both at the same time, most likely. So it really depends on what you're trying to do. But this is not what we've done. This is something that we're considering now. And at the moment, we're seeing mostly the electrical part and the mechanical, because the mechanical is a bit difficult, and the dispersion in ranges of values you can find in literature is pretty high for like diseased tissue, scar tissue, and also it's usually more evaluated in animals, not in humans, because you can't really do that very easily.
Okay, thank you for such a clear answer. We have two more questions. The first is asked by Peter Cavene. And he asks, sensitivity analysis is an underpinning for uncertainty quantification. Verification and validation are also integral in this. How do you quantify the uncertainty in your calculations? Verification means that you ensure that the software implementation is done correctly, i.e. the mathematical models are correct and correctly implemented. So how do you validate the model? Is it patient-specific matter? So I get two questions there. One is verification and one is validation.
Yeah, okay, step by step first. Okay, verification. Yeah, so verification, in a way, what you have to do is you have to evaluate your numerical model in the sense that, as you make it, the simplest approach would be, you make a mesh finer and finer and finer to see if you have conversions in results, right? That's the simplest way, or the most often used way. But, you can also measure, for instance, how tight my convergence tolerances are. That's another way. So we've actually checked in terms of convergence tolerances on time step, not like a mesh step, if you want. And we have, good conversions in results. We haven't really checked conversions in mesh, but the thing is that there's plenty of literature which support our choice of element size. So the element size we're considering is within the range of, those mesh sizes that already lead to conversions in the results for the electrical part. So that's regarding verification. Regarding validation, it is part of what we've done in terms of making sure that our QOIs lie within, clinical ranges roughly. Obviously, clinical ranges can be very dispersed, depends on how you measure them, how old they are, and what's the approach they've used. We've ensured that, so that's our part of validation. In terms of uncertainty quantification and also, if you want, sensitivity analysis, it's a sensitivity analysis approach. Uncertainty quantification, the problem with that in these sort of simulations is that we do not really have a lot of data on what probability distributions our parameters have, okay? So that's a key point. I think I'd like to address it now, maybe. I'd like to mention that and make a strong case that we do not really have proper experimental measurements of our input parameters. Because it's difficult to measure, for instance, what's the stiffness, the sort of constant stiffness around the epicurrent. That's something that is very difficult to assess. So we have assumptions of lack of knowledge in our parameters, meaning uniform distributions over a wide range. So when you do that, you're sort of not really doing uncertainty quantification, because the goal of uncertainty quantification is to go from probability distributions in parameters. You pass them through the model, and then you get certain probability distributions of your QOIs, meaning that you're propagating the uncertainty, and that's difficult if you don't have proper probability distributions of your parameters. So that's some previous work that should be done before actually embarking on uncertainty quantification. But indeed, at least what we've tried to do is have a very preliminary assessment of if we had almost no knowledge of our parameters, have wide ranges and uniform distributions, and you propagate them through the model, and these what you can do is roughly assess sensitivities. Needless to say, these sensitivities are still going to be affected by your assumptions on the distributions of in the input parameters. This is an iterative approach. You do that, and you go back and see, okay, what other parameters that are more important, and then you evaluate them experimentally again. You get more precise probability distributions, and then you run your sampling again, and so on. And then, when you have appropriate distributions for your parameters, then you can call what you're doing uncertainty quantification. But it is indeed a key point in numerical modeling. And we're just embarking on that. I cannot say that we are done on that. We actually this is an ongoing work that we will be constantly doing. Yeah. Hopefully that's what Peter meant. Hopefully the answer is okay.
Okay, thank you very much for such a long, clear answer. We do have one more question, is from Eric Lush, which I cannot see his question.
It's incomplete.
I guess, yeah, those are all the questions okay. See, he typed in multiple questions. So, so the first question he asks is, if you studied the effect of the interaction between parameters and sensitivity analysis. So this is another sensitivity analysis question.
Okay, for what we did, we assumed that there was no correlation between our parameters. Okay, that's an assumption that you have to take into consideration when you use the approach we used. Granted, there could be some correlation in some cases. Okay, but we blatantly we blatantly ignore. We assume that there is no correlation. So we assume no interaction, no dependence, if you want, on one or other parameters. And I'm speaking about the parameters, obviously, as I said, when you are talking about the QOIs, you could expect some correlation, for instance, between ejection, as I mentioned, between ejection fraction and systolic pressure, because the higher, if you're doing exercise, your ejection fraction will be higher, and then your systolic pressure is likely to be higher as well. So from that point of view, you could see some correlation with some QIs, but we assume no correlation in our parameters, in our input parameters, and hopefully this answer is also answering your question. Otherwise, you can just ask something else again.
Okay, great. He has another question, is a bit more specific.
Yeah, sure.
And he asks, which is the range of values you considered for the bulk modulus to control the compressibility? Isn't this parameter related to wall thickness?
Let's see. Yes, so this parameter is correlated with wall thickness, indeed. The values that we used, what was it? Let me see. I think we found the value of 3.3 megapascals, I think, in literature, and I decreased it to around maybe half a megapascal to 5 megapascals. So quite a wide range with uniform distribution. But it does affect your QIs. I mean, I think a reasonable assumption though would have been, if you use a model that has full incompressibility instead of partial incompressibility as this one. This one basically is just a penalty term that you include in your hyperplastic law, and then you increase your bulk modulus to sort of make it prohibitive for the model to change the volume in your system. So that's the approach we've used, but actually a more reasonable approach, maybe, or simpler in the sense that you're not considering one of the parameters would be to use full incompressibility, but it indeed changes wall thickening. Yeah.
Thank you very much. And Eric writes, thank you for your answer.
You're welcome.
We have one from Jordi Cano, and he asks, when considering the simulation space, do you set absolute or relative simulation ranges? Or did you choose a particular range for every variable?
Sorry, I was speaking with the microphone muted. So we said, can you read the first part again?
Sure. When considering the simulation space, do you set absolute or relative simulation ranges, or did you choose a particular range for every variable?
I see. Yes. So they're not absolute, and I'm going to tell you why. In some cases, so even though I said that we have, almost we're fairly ignorant about the values of some of the parameters. I mean, sorry to put it bluntly, but I mean, for instance, the stiffness of the epicardium or the pericardium is not something you're going to easily find in literature. I would say I haven't really found much about it. So we have some values that we actually have some rough idea of what's the value. So those, you can vary those values in in a relative way around the sort of baseline value that you can find in literature. But in terms of when we're actually varying our stiffness of the pericardium, we have to use range that considers several orders of magnitude. We're not really worried about sampling every specific beat, so you actually need to use a log space approximation. No, I mean it's more like from like 0 to 1 million, as an example. You have to use a very wide range so that a little bit. So the next step would actually be to focus, reduce that range and maybe change from uniform to log uniform or something that has more weight on specific parts of the parameter space. But the first approximation is, as I said, an approximation is, and for some of the parameters, including the stiffness of the pericardium, is a wide range and no baseline value, because we don't really know any baseline value. We just need to keep changing until we see something that makes sense, physiologically speaking. But as I said, in some of the parameters, we have baseline values, and we can actually have a range which is sort of centered around that baseline, around those baseline values. Hopefully, that's what you asked. But I think, yeah, it's not an absolute absolute ranges about values for all of them.
Yeah, thank you very much, Francesc. Okay, we have one more, and it's from Konstantinos Montris, and he asks, could you provide, please, some more information regarding the selection criteria of the boundary conditions on the mechanical part of the model?
Okay. Just a second. Here. Okay. Can you please repeat the question?
Yes, of course. Could you provide, please, some more information regarding the selection criteria of the boundary conditions on the mechanical part of the model?
Okay. Okay. Yes. So 3 things, let's say. The first 2 is on the endocardium, on the inner part of the ventricles, if you want, pressure. Okay. Just a constant pressure. So the wing castle imposes the same pressure everywhere on the endocardium. So that's for the pressure. Then the elastic foundation is basically a bed of springs, if you want. It's like a spring support for the whole pericardium that has a constant stiffness. Okay, that's the one of the parameters that we included in the sensitivity analysis. And one might argue why constant and not varying. Yes, but then it would be adding more uncertainty and probably more parameters into our model. And we, as I said, I do not even know the value of these constant stiffness, let alone the values of several stiffnesses, or or sort of a parameter that defines how this is inhomogeneous across space. So that's how it's been defined. And then the third thing would be this is a dynamical model, so there's no need to impose any essential boundary conditions. That your matrix is already positive definite because of the effect of the mass matrix on your system. So we didn't need to fix any specific displacement on any specific node for that. It's actually well defined, well solved, without imposing any essential boundary conditions. Yeah. So has this answered your question?
I will assume that this is a decent answer. I mean, I think there were quite a few questions regarding parameters, and this one is a bit specific to the material model.
What is the question?
Oh, Konstantinos, about the boundary conditions for the mechanical model.
Yeah.
I assume that this.
Look, if you want further information, just drop me an email.
Of course.
You really need anything very specific, but what I can say about how we impose or how we model these is precisely like this. A pressure which is defined through a wing castle, an elastic support, which is basically just a bed of springs, and then no essential boundary conditions because we're actually solving this system dynamically. So the fact that we have this dynamical bit, these inertias, allows you to not impose any essential boundary conditions. And yeah, if you have any more specific question, please drop me an email. That's perfectly fine.
Okay, thank you very much, Francesc. At the moment, we have no more questions, which, I mean, there were a lot of questions, so thank you very much for everybody's participation. I just would like to thank Francesc one more time for such a great talk and a lot of questions. And I would like to remind everybody that the recording of this webinar will be put on the CompBioMed website. So if you happen to if you want to go back and listen to the talk or any of the questions, you can do that there. So I think this officially brings the completion to the 7th webinar, and I would like to thank everybody's participation. Okay, so goodbye, everybody.
Thank you and goodbye.